next step, and we'll just get, we'll jump into this. We're not obviously going to get all the way through it, but we'll make some progress. Evaluating limits analytically. Okay, so we talked about how we can use graphs or tables to either graphically or numerically, we can evaluate limits. But that's a little bit unsatisfying because we're always kind of having to make approximations based on the behaviors, the trends in the table or in the function. But sometimes that can miss important behavior. Okay, it's a good tool, but it's not going to give us necessarily exact answers that we can take to the bank that are absolutely guaranteed to be true. To do that, we need to actually do some algebra, right? So we're going to need to learn how to evaluate limits analytically to get exact answers, not just decimal approximations. So let's talk about this a little bit. So first of all, we're going to look at some properties of limits. You want to be familiar with these, but they're very intuitive. Once we've talked through them, they'll just make sense, and it's what you would expect to happen. So first of all, when we're going to attempt to evaluate a limit analytically, we always start by trying direct substitution or direct evaluation, which literally means we're just going to see what happens if we plug the value into the function. Okay. If the function is continuous, now what does it mean for a function to be continuous? We defined that a couple of years ago, and I'm sure you talked about it about 1,000 times last year. What does it mean for a function to be continuous? Say it a little louder. Goes on forever, okay, but there's something more to it. Something more to it. You can think of it in terms of what it would look like if I were to graph the function on the board. If it's continuous, if a function is continuous, when I graph it, what is it going to be? What do you mean by repeat? Yeah, well, maybe not. That's not essential. It's possible, but it doesn't have to. But when I graph it, there's something about when I put my pen on the board, if the function is continuous and I make the graph, what can you tell me? Does my pen ever come off the board? No. If it's continuous, I can graph it by putting my pen down once and never taking it off the board. Okay. If there's a discontinuity, that means I have to pick my pen off the board for at least one point. Even if there's a hole in the function, technically, if I'm graphing a function with a hole, I've got to pick my pen off the board, skip over that hole, and go to the other side, right? Does that make sense? Or if there's a break in the function, I pick my pen off the board and I have to move it quite a bit. Or if there's a vertical asymptote, I have to move my pen infinitely far, right, off the board. Okay, does that make sense to finish graphing it? Okay, so a continuous function is one that I can graph without picking my pen off the board. It's defined every place, but I don't have to pick my pen off the board. So for any function that is continuous, think about this now. If I've got a continuous function, let's look at a quick example of one. One I can graph without picking my pen off the board. Wouldn't you agree that as the ant approaches a value C, the ant is always going to anticipate stepping on the place where he really would step if he took that last step? Does that make sense? The limit of the function is always going to equal the value of the function at that place if the function is continuous, right? Because if I'm not picking my pen off the board to graph this thing, how could it be any other way, right? Okay, so if a function is continuous, direct evaluation or direct substitution will always give us the answer very simply. If you want to answer the question, where does the ant anticipate stepping? The easiest way to answer that is to simply ask, well, where does the ant actually step? Because that's where he's going to end up, where he thinks he's going to end up. The function's continuous. He can't go anyplace else. That's different than a function that's discontinuous. That's where things get a little bit tricky. If I have a discontinuous function, then at this point right here, okay, that's not going to work now. right? Now there's a discontinuity. The ant thinks he's approaching here, but the function actually exists there, right? Or another one. Here, let's draw a different one. How about this guy? Again, that's a discontinuous function. I have to pick my pen off the board to graph that point, right? The ant approaches a value that's different than where he actually ends up when he takes that last step. If it's continuous, though, he always ends up right where he thinks he's going to go. So all we have to do to evaluate the function is plug in the value that we're approaching and see where it actually is on the function. If a function's continuous, the limit of f of x as x approaches c is guaranteed to be at f of c. Okay? Does that make sense? Give me thumbs on that. How are we doing on that? Okay, all right, all right. So let's look at some, this sentence is really important here. Such well-behaved functions are continuous at C. Those are the ones where direct substitution is guaranteed to work. Okay, it's all the other ones that are tricky. Those are easy. Let's look at some basic examples, right? I don't want to spend too much time on this because it's really not that big a deal, but let's spend a little time. So what about these? These are some basic limits that you need to be familiar with, but they're really obvious. If we take the function f of x equals b, like in this first example, right? This example right here, f of x equals b. The limit of f of x, when f of x is b, as x approaches c, is what? Well, what does the function f of x equals the constant b look like? Looks like that, doesn't it? Right? So if I pick a value c, let me do that. There's a value c. I'm just going to pick the value 3 in this case. Okay, so c is out here. There's x equals 3. That's the value we're going to approach. As I drag this function towards 3, well, what y value do you think the ant anticipates stepping on? 3, right? It's just a constant horizontal function. And when we get there, what value is the ant going to have? Well, it's going to be right on 3, isn't it? Right? Because the function is continuous. So the ant's going to anticipate stepping on that point right there, and he's going to, because the function is continuous. He always steps where he thinks he's going to step. Okay? There's no tricks on that function. Okay? How about the function? Let's look at this next one. So the next one is the function, the limit of f of x equals x. Okay, isn't that just a diagonal line with a slope of 1? If we graph that function, oops, I want to make, I got to go down here and fix this. Hang on. Looks like that, doesn't it? Right? And again, as we approach x equals 3, what's the y value going to approach? Well, 3. Agreed? Because the function is y equals x, f of x equals x. So as x approaches 3, f of x approaches 3. Agreed? So again, direct substitution is always going to work, and the answer is always going to be C in that case, because the function is just the line y equals x. Okay. Well, what if we took the third possibility? What if we took the limit of x to the n as x approaches c? Well, again, x to the n, we can look at the graph. That again is going to be where can I do this? Well, I guess we'll have to do it right there. X to the n is going to be another function guaranteed to work. This time I'm just going to let's make it n squared. How about? There we go. There's x squared. If I graph my function, and again, as the ant walks up towards x equals 3, Well, what y value is he approaching? 3 squared, right? Approaching 9. And where's he going to be when he actually gets there? He's going to be on the point 3,9, right where he thinks he's going to be. Okay, that would work for any power of x, not just x squared. And so we know, therefore, that the limit of x to the n as x approaches c is just c to the n. I'm just going to directly evaluate. I'm just going to plug in that value I'm approaching for x. That's the answer. Okay? Okay, we're going to look at, it works for all the easy limits to take that are trivial. Direct substitution will work on, and you're done before you even start. It's the other ones we're going to spend a little time on. So some other properties of limits. The scalar multiple. If you're going to multiply a function by a constant, we call that a scalar multiple. So if we're going to make some definitions here, we're going to say, let's let b and c be real numbers, let n be a positive integer, and let f and g be functions with limits L and K. So in other words, the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is the number K. Okay, then if I take the limit of b times f of x as x approaches c, that's really just the same thing as taking, in other words, what I can think about doing here is taking that b, oops, don't do that. Let me freeze that thing so it doesn't move. There we go. I can think about this as pulling that b outside of the limit. Okay, and what I end up with, the limit of b times f of x as x approaches c is just b times L. Okay? So multiplying a function by a constant just multiplies the corresponding limit by the same constant. Okay? What about a sum or difference? If I have the limit of f of x plus or minus g of x, the limit of that whole thing, well, I can just treat those as individual limits. I can take the limits one step at a time. I could make that the limit of f of x, which is L, plus or minus the limit of g of x. Okay? So that's a sum or difference property. Product. If I have the limit of a product of functions, that's equal to the product of the limits. Okay? Same thing with a quotient. As long as the denominator is not 0, the limit of a quotient of functions is equal to the quotient of their limits. Super easy. It's just exactly the way you think it would be. Works for a power also. The limit of a function to a power is equal to the limit to that power. Okay? All right, so let's look at an example that's a polynomial. Find this limit. Polynomials are always continuous, right? So you know that you can always evaluate a polynomial using direct substitution. So what are we going to get here? If I take the limit of the polynomial 4x squared plus 3 as x approaches 2, what do you think the answer is going to be? We're asking the question, where does the ant anticipate stepping when he's walking along this polynomial function as x approaches 2? How'd you get that? You're right.
I just put the 2 in.
That's it, right? We just plugged it in. We just get 4 times 2 squared plus 3 equals 19. Okay, without even thinking about it, you just used several of those limits. Okay, like look what we did. We took the limit of a sum and we didn't split it into separate limits. We didn't need to. We just evaluated this thing directly. Okay, we really technically had the limit of 4x squared plus the limit of 3, but we don't have to do that. We don't have to do that. We can just treat it as a limit of that whole sum. Okay, and that's what we got, right? There's a bunch of properties that you didn't even think about that are just completely intuitive, but you used them without even thinking about it, which is good. Okay, direct substitution property is valid for all polynomial and rational functions with non-zero denominators. Let's look at an example of a rational function. Remember, a rational function is just a ratio of polynomials, polynomial divided by polynomial, right? So then if I have something like if r is a rational function defined as r of x equals the polynomial p of x divided by the polynomial q of x, then if we approach, as x approaches c, the limit of r of x is just going to equal r of c. Direct substitution is going to work as long as q of c is not equal to 0, because that would be a place where a rational function would have a vertical asymptote, right? Okay. So let's try one here. How about this guy? Do this one. You do this in your head. What's the limit of that rational function as x approaches 1? Yeah, right? How come? Because we get 1 squared plus 1 plus 2 over 1 plus 1. Well, that's just 4 over 2, which is 2. Okay? Direct substitution always works for polynomials and rational functions in the domain of the rational function, where you're not dividing by 0. Okay? No big deal. The same thing works for radical functions. Okay, and I'm not going to show you graph. I graphed some, but you don't even need to see them. You know that we know that any radical function in its domain is going to be continuous, right? What's a square root function look like? Let's just look at the shapes of a couple of these, and that'll be sufficient. So a square root function just looks like that, right? Cube root functions going to look like that. Fourth root functions going to look like that. They're all going to be continuous where they are graphed in their domain. So therefore, we can take a limit of any radical function using direct substitution. Okay? What about a composition of functions? If f and g are functions such that the limit of g of x is equal to L, as x approaches c, and the limit of f of x is equal to f of L as x approaches L, then we can make a composition from this, right? We could say that the limit of f of g of x as x approaches c is equal to f of the limit of g of x as x approaches c, which is just f of L. Okay, that's easy to do. That sounds complicated, but here's an example right here. Let's look at this guy. What if we wanted to do this problem? If we want to evaluate the limit of x squared plus 4 as x approaches 0, technically that's a composition of functions. On the outside, it's a square root. On the inside, it's a polynomial x squared plus 4, right? So technically, the limit of x squared plus 4 as x approaches 0 is equal to 0 squared plus 4, which is 4, right? The limit of the square root of x as x approaches 4, why 4? Because that's the output of the inside function, is equal to 2. So that's our answer. Do we have to make it that complicated? No, you don't at all. You just use direct substitution on the composition. If I take that whole big compositional function and I evaluate that as x approaches 0, what do I get? The square root of 0 plus 4 is 2. Done. Okay? It doesn't need to be, you don't need to make it complicated. The limits are very intuitive and simple. Same thing down here. If I'm taking a limit of this cube root of a polynomial, well, I just evaluate the thing as x approaches 3. Okay, plug in 3, get an answer. Okay, so what we get out of this? Oh, same thing with trig functions. All the trig functions are continuous on their domains. So you can always take limits of trig functions using direct substitution. Okay, so in each of the previous examples, direct substitution worked. Okay, that's easy. What happens if it doesn't work though? So this is a really important page. This is the page that all this stuff you're going to go, I got it. This all gets really easy right now. Okay, what do we do for finding limits? We're always going to attempt direct substitution first. Okay, direct substitution will work if the function is continuous. Okay, or at least if it's continuous on the interval where x is approaching a value. Okay, so either it's going to work or it's not. If it works, you're done. If you try direct substitution and you get an answer that's doesn't necessarily be a fraction technically, but if you get an answer that's a real number not divided by 0, you're done. That's your answer. Move on to the next problem. For example, let's put an example of each of these things here. So the limit of sine x squared as x approaches 0. Well, I try to evaluate directly. If I evaluate directly, I get sine of 0, which is 0. I'm done. I got a number and I didn't get a 0 on the bottom. Okay. Another one. The limit of x squared plus 3 over x minus 4 as x approaches 1. What do we get? Well, I'm going to get on the top, I'm going to get 1 squared plus 3 is 4. On the bottom, I get 1 minus 4 is negative 3. So I get negative 4/3. Done. I got an answer with no zeros on the bottom. Okay? Make sense? Those are the easy kind. Okay, sometimes that doesn't happen though. Sometimes we're not so lucky. The other possibility, all the previous examples we've looked at have fit that pattern. Direct substitution has worked. We're done. Okay, another thing that can happen though is direct substitution might fail. We might get an answer like a number divided by 0, where the top of the fraction, a over 0, where a is not equal to 0. We get some non-zero number divided by 0. What does this mean? Limit doesn't exist. We'll get more specific with that later, but for now, no limit. Okay, that's the answer. You're done for now. Later, we'll be a little more specific with that. But you're done. Those two are easy. They're quick. Either you get an answer with direct substitution, or in type 2, you get an answer that's where you get a 0 on the bottom and there's no limit. Done. Okay, here's the kind that takes a little more work. The third type is, well, here's an example of that one. Okay. We haven't seen any like this yet, but what if you had something like the limit of x minus 5 over x plus 2 as x approaches negative 2? That's going to give you negative 7 on the top and 0 on the bottom. Explodes. No limit. Okay. What's happening there, as we're going to see later, that rational function has a vertical asymptote. So we know limits don't exist at vertical asymptotes. But we don't have to think about that. We just know if we fit that pattern, it doesn't exist. Okay, here's the third type. This is what we get to if direct substitution doesn't work and the function doesn't have a 0 on the bottom and a number on the top. We can get an answer like 0 over 0. That's different, right? Part 2 was a non-zero number divided by 0. If I get an answer like 0 over 0, or later in the course, infinity over infinity, or even something like 0 times infinity, but that's way in the future. For now, we'll just stick with this, 0 over 0. This is what we call an indeterminate form, and it means more work. So that limit might exist, it might not exist, but we got to do some more work to find out which one of those things is happening. Okay, so again, let me make this a little smaller so you can see this whole thing. There's the three possibilities. That's our strategy. Attempt direct substitution. If it works, you're done. If it fails and you get a non-zero number over 0, you're done. No limit. If you get an indeterminate form like 0 over 0, then we got to proceed to some specialized algebra that we'll talk about Tuesday. How about? Okay? Have a great weekend. I did. What's the due date on it again? When do you need it? For a while, like a month or more.